And it has like 10 mini games. So since we had 5 weeks, what we did, we looked into our bag of tricks to see what we've done before.
Isn't that like the same game?
Pardon me?
This like the same game and just covered and nothing.
This is stuff that we both had sort of lined in the back from stuff we've done years past. Crosstown. I like this one.
Robots ready?
So if you saw the movie, this is actually from the movie. There was this Crosstown Express. You had to ride. What you have to do is hit these balls. So anyway. So I spent like 2 out of 5 weeks. I was going to do a whole game based on putting logic circuits together and solving puzzles and opening doors and stuff like that. And after 2 days, it was the biggest, fattest mess. And we both just decided we don't have time to work on this. But it would be a really cool idea for a game. Maybe one day I'll figure out how to make a game out of it. You want me to worry about one more thing?
Yes.
Anything but that crap we're supposed to learn. So, this actually was an iPhone app that I did. And about a year ago, Microsoft paid me for a series of articles to talk about how I took an iPhone app and converted it to Windows 8. So if you point to it, and if you don't know how to play, so anyway, that's chess kids. Crap. Oh, you don't know how to even up your own game, Rick. Did it quit?
No.
Well, it's somewhere. So anyway. So one day you'll see my logic meeting out there. Okay. Any questions on this part of it? Pretty easy. Good. Let's go back and do some more fun stuff. Okay, so you got that. Now, if I ask this on a test, I will ask this on a test. You guys will all get it right, correct? Okay. Okay, this will definitely be on your test. Guaranteed. Okay, so here we talk about the order of operations and the precedence, which I've already mentioned. I was ahead of myself. Not is always, well, parentheses is first, not, and then and or. And that's how we know what goes in those intermediate steps. Okay, so digital computers, that's what they use. I mean, like even the output to your modem or the output to your speakers or whatever uses these digital circuits to make decisions. Yeah, probably not the output to your speakers, but most everything else. So what's the deal? Do we want circuits this big, or do we want those circuits that goes behind your ear? Yeah, behind the ear. That's what I'm waiting for. The circuit goes behind my ear. Then I can find my way anywhere, get my answers to anything. Is Siri pretty good, by the way? When you ask Siri, it's not good? No. When you ask it a question, it searches the internet, it's not good?
Because it's understanding what you're saying, ever.
What now?
You never understand the word you're saying.
It's got that straight points.
Really? Well, I only use my Siri for one thing, get directions. It's good at that. It's really good at that. Or I'd be lost forever. Because before Siri I was. But the point is we want the smallest, cheapest, simplest circuits possible. Okay, so we're gonna have less, remember we already talked about power consumption. So the smaller and simpler, the less power they're going to consume. They're going to be cheaper to manufacture and so forth. Okay, so we always need to reduce what we're doing if at all possible. Now, you guys have had trig, right? And you had those trig identities, right? And when you were at trig, did you wonder why you had to learn those stupid identities? You did? You wondered? Well, when you got to calculus 1, did you realize why you needed to memorize them? Because in calculus 1, when you reduce things, you use those triggers. Okay, so you guys, what now? You guys not had calculus? I thought it was.
Only CS has to take calculus.
Okay. Imagine you remember calculus. When you finally get to calculus, all those trig identities you were supposed to learn help you in calculus because they help you reduce expressions. It's the same thing with Boolean algebra, is that we have these identifiers that help us reduce things. Okay. So 1 and x is always x. 0 or x is always x. So you can actually reduce it from 2 to 1. Null law. 0 and x is always 0, 1, or x is always 1. Okay, I'm not even going to try to pronounce that next one. But it's really useful because you can definitely cut your circuits in half if you have xx or x plus x. Right? It's not 2x. And then the inverse law, okay? So let's take a look at why that is. Let's go ahead and make some truth tables and figure out why this identity actually works. Okay. So, first we have identity. Bless you. 1x equals x. 0 or equals x. Why? Let's make truth tables for these. 1, 0, 1, 1 are the only two choices you have, right? Right? Okay. If x is 0, you're always going to get 0, right? If x is 1, you're always going to get 1, correct? True or false? Which means the answer of 1x, 1 and x is always going to be whatever x is. Okay? And over here, your choices are 0 or 0, 0 or 1. In this case, you get 0. In this case, you get 1. But in both cases, whatever you get is the same as x. So that's the first. Okay, the null law. So that's 0 and x equals 0. 1 or x equals 1. So your only choices here are 0, 0, 0, 1. In both cases, it's going to be 0. 1 or x, 1 or 0, 1 or 1. They're both going to give you the result of 1. That's a useful identity. The idempotent law. X equals x. X and x equals x. X or x equals x. So truth table on those. Okay, so your choices here are 0, 0, or 1, 1, correct? Those are your only two choices. This is going to equal 0, and this is going to equal 1. But in both cases, it was the same as whatever x was the answer you got. And on or, you're either going to have 0 or 0, 1 or 1. Both? 0, 1. And in both cases, x is going to equal whatever the output is. And the last one is the inverse law. X not x. I sure can. X not x equals 0. And x plus not x equals 1. Okay, so I only have two choices. 0, and what's the not? The complement. Or 1, and the complement of that, right? It's always going to equal 0. And here, you have 0 or the complement, or 1 and the complement, and it's always going to equal 1. So those are those identities. Those are in the book somewhere. Okay, so back to the book. I know most of you probably haven't bought the book, right? It's okay. So did you get the PDF somehow? Do you all have at least a PDF? Can you please read 3.1 and 3.2 in the PDF? Because this is all covered in there. So go ahead and read that. I'll pretend like you have a book, and we'll just go ahead and work. I've got the PDF and this, and it's the same material. What I'll do for the assignments, I'll just take it out of the PDF, copy it out of the PDF, and put it into the web course. Okay. Okay. Okay, so you got those identities. You see how I'm getting them? You see how I'm proving them? Okay. Now, you had to have these laws. What grade did you get these laws? 4th grade or something?
Remember that?
What now?
Probably less than, it's earlier than that.
Earlier than that? You must have been smarter than me or something. The only weird one is the distributive and. I mean, you gotta get the commutative is really easy. Associative is really easy. But I think the one that isn't like instinctively obvious is the distributive one. So let's go through that. Let me just write this down before So we have x plus yz equals y. Okay, so that's and. Now for or, we're going to have Okay, so in this top one, to me it's not intuitively obvious that how we get from there to there. Okay. But if we split these up, let's go and do a truth table. See if we can squeeze this in here. Should give myself more room. God, got it. Yeah, well, I'm not gonna try.
Shrink.
Shrink. What is a superhero that can shrink? Okay. So let's do YZ first. Y and Z. Let's see, 0, 0, 0, 1, 0, 0, 0, 1. That looks like crap. X or YZ. So now I'm going to take the X column and OR it with this column, right? 0, 0, 0, 1, 1, 1, 1. So that's, oh yes, Okay, so that's how we get that. The bottom one I have totally obliterated, haven't I? Okay. Now, one of these laws, you get the double complement law, right? Okay, and the absorption law is pretty easy. But that De Morgan's law, I actually wanted to show you how that works. I actually use De Morgan's law all the time in my program. So not x and y. And notice it's not the whole thing, okay? It's not like each x and y is not. It's like it's the complement of the results of x and y, okay? Equals not x4, not y. So what I do in my programming a lot of times is I have I might have a screen where I'm testing. And I want to know if the mouse hovers over this. Okay. And the mouse coordinates always start up here, 0, 0. Let's say you have a big very big screen. You might have like 1920 by 1080. Okay? So going this direction, yeah, sorry. So going this direction are my x coordinates, going this direction are my y coordinates. Okay. So in order to know if the mouse cursor is inside of that rectangle, I say, let's just say mx is mouse, my is mouse, y. And let's say that's at 1100, and that's 1150. And that's y equals, we'll say 600, here y equals 500. So to find out if the mouse is between there, I say, if mx is greater than or equal to at 1100, and my is greater than or equal to 500, and mx is less than, what is that, 1150, and my is less than 600, blah, blah, blah. I might do something. But what if eventually the logic changes and I want to know when it's not in the rectangle? So is this a hard change to make? Okay, all you have to do, it's real easy. We use that's De Morgan's law. We put everything in parentheses and change from and to or, and just put a not in front of it. I actually have a demo to show you where I did that to show you. Okay, so here I'm testing to see x is greater than the rectangle left, x is greater than the, y is greater than the rectangle top, and so forth. But now I can just reverse the whole thing by knotting the or, and that's exactly that De Morgan's law that we talked about. Here you see what I mean. Here it's going to give you the results over here. You notice for both of them, both you get the same result, whether it's in or out, whether you're using the and or the not ors. And then it changes, and it changes. And I end up using De Morgan's law all the time in my own program. So. Probably use it in robots. Okay. Let's see. So here's a you will not be responsible for doing this on your test. But I just want to show you this example because it's pretty cool that you can go from a fairly complicated example, f of x, y, z equals that expression up there. And by going through each law, each identity, you get down to x and z. That's pretty cool. Okay. So anyway, obviously, it's gonna be cheaper to have a smaller circuit. And what this is saying is many times the knot is better and cheaper to build than the true segment. Yes.
If x plus y is x and y, what's x y?
Let me write that down because I'm not sure I got it. I'm gonna write that down. Okay. Give it to me slow.
X plus y.
X or Y.
Oh, okay, so that's 4. And then x, y.
X, Y is and. So it's X and Y.
Okay, so plus 0.
Is that it?
Yeah.
Okay. So we call these synonymous forms or sometimes logically equivalent. So then we get to this whole idea of standardized or canonical form, which, oh nice PowerPoint slide there. Lovely. So that's the canonical form, which you are not responsible for that. I just want to say. Okay. And you won't be responsible for that either. Okay. Questions? Questions on the rainy Monday after our test. At least you didn't shut our light down. All right. So what we're going to do on Wednesday is we're going to do more of the same, except we're going to continue on with the board.